In section 1.7, we started getting at the idea of what it means for two different graphs to be structurally the same, or essentially the same, or structurally different from each other. Now remember that technically the way we describe graph equality is we would say that two graphs are equal to each other, that G is equal to H, if and only if G and H have the exact same vertex set and the exact same edge set, right? The exact same vertices, labeled exactly the same, and the exact same edges, right? But that's not always a very meaningful definition of sameness because, for instance, sometimes we draw graphs without labeling them, right? Without actually labeling the vertex set. And sometimes, you know, we would want to say something like this graph. Let's say this is A, B, C. This is the graph G. And then maybe this is the graph H, but I've labeled it now BAC. These two graphs really are the same graph, right? And in any of the properties that kind of matter, they're the same, right? It's a path of length 2. But they don't have the exact same vertex set and edge set because, for instance, AC is not an edge in this graph, but it is an edge in this graph, right? So graph equality is not always the best way of describing what it means for two graphs to be structurally the same. And so this sort of gets at a different idea of what it means to really describe two graphs as having the same structural properties. And as an example, these two graphs here are drawn pretty differently, but actually structurally are the same. In other words, we could find a way to label these vertices so that they're the exact same as each other, right? I'm going to label this vertex here A. This is the only vertex that we can sort of right off the bat say they have to be equal to each other, since these are the only vertices in each graph of degree 1. So with that in mind, the only neighbor of this vertex is this one, and similarly, the only neighbor of this vertex is this one, so I'm going to name both of these B. And from here, this vertex B has two other neighbors, and it's sort of symmetric from here, so it doesn't really matter what you call them. I'll call one of them C and one of them D. And then finally, we just need to make sure that we label these last two in such a way that the neighbor of D's match up and the neighbor of C's match up. So maybe call this E, and this last one F. So it's possible for us to label these in the same way so that it's the exact same graph, right? So that it has the same vertex set and the same edge set. But what if your two graphs are already labeled and they don't have the exact same vertex set and edge set? We know that it's possible for them to still structurally be the same like we saw up here. And so to define a graph isomorphism, we're going to say that two labeled graphs, G and H, are isomorphic to each other if there's some bijection, we'll call it phi, this is a Greek letter phi, from the vertex set of G to the vertex set of H that preserves the edge relation. In other words, UV is an edge in the first graph if and only if its image in the second graph is also an edge, right? So if U is adjacent to V in this first graph, and you look at the map from the first graph to the second graph, the images of those two vertices, phi of U and phi of V, have to be connected in the second graph, right? So this is what it means to preserve the edge relation. And it goes backwards as well. If you have an edge in the second graph between phi of U and phi of V, then its pre-image, U and V, have to be connected in the first graph. If this is true, if such an isomorphism exists between these functions, we say that G is isomorphic to H. And one thing that I also want to just emphasize here is that this has to be a bijective function. Remember, bijection means it's one-to-one and it's onto, right? And so in particular, there have to be the exact same number of vertices of G as there are vertices of H, and your function needs to be one-to-one and onto. So every individual vertex of G needs to map to its own unique output in H. So let's try to describe an isomorphism between two graphs. So I have these two graphs down here. I claim that they're isomorphic, that they're structurally the same as each other. But to prove it, we need to find an isomorphism from one graph to the other. All right, now notice that these graphs have a lot of symmetry here, right? It's hard to really differentiate any one vertex from the other. So it shouldn't really matter how you map your first pair of vertices. So if I start with A and I want to define phi of A, if I want to map this to something over here, it shouldn't really matter which one, so I'm just going to say phi of A is equal to 1. But after this, we have to be careful about how we describe them. We can't just say A maps to 1, B maps to 2, C maps to 3, D maps to 4, etc. That's not going to matter. It's not going to work. It's going to be a bijection in the end, but it's not going to be an isomorphism because it's not going to preserve the edge relation. Right? I know that that wouldn't work because if I tried to, let me just do a practice one. If I tried to say that phi of B was equal to 2, we would have a problem because 1, 2 is an edge in the second graph, but AB is not an edge in the first graph. And this map needs to preserve the edge relationship, so this is not going to work. All right, so to help us figure out what this isomorphism should be, I'm going to try to use the fact, sort of reverse engineer it based on our knowledge that this has to preserve the edge relation. Right, so I know that phi of A got mapped to 1. So A is going to be adjacent to these 3 vertices in the graph. It's adjacent to E, to D, and to C. And in the second graph, the vertex 1 is adjacent to 1, to 6, and to 2. All right, and so if I want to try to define this map from here, let's try to decide what phi of E, phi of D, and phi of C should be. You can try to use guess and check and see if it works, but I'm going to think ahead a little bit and say, since E, D, and C have to map to 6, 4, and 2 in some order, my leftover vertices in the first graph are going to be F and B, and my leftover vertices in the second graph are going to be 5 and 3. Notice that the only vertex out of these 3 that are adjacent to F and B would be the vertex D, and the only vertex that's adjacent to 5 and 3 in this graph would be the vertex 4, which suggests to me that this vertex here, D, is going to have to match to this vertex 4. That's the only way that we're going to preserve this edge relation. So I'm going to say that phi of D is going to have to map to 4. And from there, based on the symmetry, it's probably fair to say that either one of these would work. So I'm just going to say that phi of E is going to map to 6. And phi of C is going to map to, what's my leftover one? 2 here. Right, and now all that's left is I need to define phi of F and phi of B. And I need to make sure that I'm doing this in a way that's going to preserve the edge relation. All right, so think about what we have here. Try to use another color. We need to make sure that whatever we map F to, it's adjacent to D, to C, and to B in this graph. And D, C, and B, its image in this graph is going to be D, C, it's going to be 4, 2, and one of the other ones, right, 3 or 5. Well, the only one of these leftover vertex that's already going to be adjacent to 2 and to 4 would be this vertex 3. So I'm going to make sure that F gets mapped to 3. And so then it'll work that F of B is equal to 5 because those are our leftovers. And you can check to see that this function actually does preserve the edge relation, right? So if we were to choose any arbitrary edge here, let's say E to B, well, E gets mapped to 6 and B gets mapped to 5, and 6, 5 is indeed an edge here. To really prove that this is an isomorphism, you would have to check this for every single edge, which is a little bit tedious, but I trust that you can do that, right? Go through and check, all right, EA is an edge, and 6, 1 is an edge. Okay, go through every single edge and make sure if it's an edge in here, then its image is also an edge here, and vice versa. That's how you would check that this is an isomorphism. So this is a little bit tedious to do, and in the next video we'll talk a little bit about how you can tell in general whether two graphs are isomorphic without forming an isomorphism.